Okay, let's continue with this final part of today's presentation, where I'll present the details of numerical analysis, the analysis that's performed for this particular case study, and that was used, and some information when defining the design solution. So the numerical part of the calculation included the back analysis details, but in two for two conditions. The first condition is the condition before failure. This is the condition shown here. As you can see, the cracks were recognized here, and this is safety factor equal 1. Another safety factor equal 1 was recognized in this, and the condition after construction of this reinforced earth fill. So we have two back analyses, the first one before the construction and the second one after the construction of this, when the failure, and this is recognized here as failure plane 1, failure plane 2. So this is some failure plane that exists even before the construction, and this one did not exist before the construction. It was introduced after this surcharge applied at the top of the slope. Uh, so this is here, safety factor equal to 1, and this is some failure surface that was recognized here. Later, after the construction, we also have safety factor 1, but for this deep-seated sliding. And this result really agrees well with the cracks observed here and with this part separating from the tunnel that is on the stable ground. But this is sliding, so this is moving down the hill. So the back analysis confirms the conditions observed at the location. This is a typical 2D model that now introduce the structural element that are used for the increment of the safety factor. So this is the safety factor equal 1 without piles, capping beams, and anchors. After the piles, capping beam with anchors, we need to increase the safety factor from 1 to some value that is over 1.25, since Eurocode standard was used for the calculation, for the some norm standard for the that define the safety factors. What was used here? It was the shear strength reduction technique was used. There is no analysis performed by limit equilibrium method, only phi reduction, shear strength reduction technique, so-called shear strength reduction technique, implemented in the software Pluxee was used for the calculation. Here, following section, a lot of details of the numerical modeling were presented. I'll not spend a lot of time and details to discuss about it. You can check it. You can check it in your office if you're interested. If you need to do some similar calculation, what is shown here is the modeling of the piles. The piles are uh, constructed on some spacing. What we do in 2D modeling is that we need to model it with appropriate 2D element, since we are doing two-dimensional analysis. We also must introduce the modeling of the geogrids, since this retaining wall slope is actually a reinforced earth wall. So we need to define some stiffness of the geogrid that is defined as the ratio of the force per meter width divided by the typical deformation at yielding, that is in the range of 5 to 10% for the polyethylene geosynthetic geogrids used as the reinforcement. The anchor length of the bonded part of the geotechnical anchor was calculated by the suggestions given by this empirical diagram that shows us the link between the anchor length and average bond stress along this bonded part of anchor. So this is when you push it here, you have the resistance at the contact between the grout body and the surrounding soil. That average stress is in the range of 300 kilopascals, and it needs to be multiplied by the cylinder surface to get the ultimate pull-out force of the anchor. Here are the soil rock parameters that are defined primarily on the basis of Beck analysis, especially for this damp soil and highly weathered rock. So these set of parameters, this cohesion value, internal friction value, were defined according to Beck analysis results. So these values combined with the water level assumed in the calculation must result in the safety factor equal to 1. The marl as a bedrock material, parameters and backfill material were selected according to some empirical correlations for some experience with those material from the other design. Here are the numerical analysis result of the remediated slope. Here you can see some calculated displacements after the construction of this retaining walls with piles and anchors. So what is done here in this simulation? In this simulation, the conditions are changed in comparison to the real problem. It was actually done that in first phase, the piles were constructed. The piles and ground anchors were constructed. And after that, this reinforced earth slope was constructed as a surcharge that introduces some lateral displacement and bending moments in the piles and tension in the anchors. So the phases were changed in comparison to the real-time thing. After that, it was predicted that only half a centimeters of lateral displacement could be expected due to construction of this. The safety factor calculated by shear strength reduction technique is in the range of 1.35. That is over higher value than the target safety factor, but the failure surface looks like this. So the possibility of sliding like this is even higher than 1.35. We don't know how much higher, since we can only get the critical failure surface. But since this value is already 1.35, we are sure that this one is even higher than 135, so we can say that this supporting measure are appropriate for this problem. As you can see, in this calculation, additional conservative measure was to remove all this material here. That's actually a possible scenario in real-time world, since the stability of this dump material is not appropriate. The safety factor of this remains in the range of 1.0. So it is possible that this will continue to creep down the slope. And after 10, 20, 30 years period, there could be no, it is possible that there is no contact between this soil and this pile wall. So this was removed as some additional conservative assumption in the calculation to get and to cover the most inappropriate scenario that could occur at the location. Even then, we have the appropriate safety factors and very little horizontal displacement that will not influence and cause any cracks here at this wall. Additional detail shown here is a reinforcement detail for this 60 centimeter pile, so you can see what the reinforcement was calculated according to calculation result. What I would also like to mention that the monitoring was applied here, and actually 1 inclinometer was installed in one of these piles constructed here. I think it was here. So during the installation of these piles, inside the reinforcement cage, an inclinometer was installed, and the initial reading was performed after the construction. Later, after half a year, 1 year, few series of measurements were also applied, and no indication of any displacement were observed. That means that this solution could be considered as appropriate for this problem, and there is no additional problems with this part of highway route. Of course, even if you go for some visual observation, you will see there's no any cracks at the facing in this wall. Some conclusions from this case study could be that the suggested solution requires special geotechnical construction equipment for construction of pile and anchors. After the construction, there is no indication of some extensive lateral displacement or sliding at the location, and that's good. That shows us some courage to see that these applied measures are appropriate for this problem. One shortage that could be defined for this solution could be a durability of the geotechnical anchors. However, a long-term geotechnical anchors were implemented here, so it's expected that no corrosion or something else will occur in the serviceability period of 50 or 75 years. However, if some indication of displacement is recognized in the future, some additional anchors could be drilled to the capping beam and installed in the future if necessary. That's why it's important to enable the continuous monitoring to decide if it's necessary to go for the replacement anchors installation at this location. Since this was constructed only 5 years ago, of course, it's still too early to discuss about this aspect of the construction. Okay, that was everything we planned to discuss about for today's lectures. Next week we'll go for details of the case study 2, and we'll define some conclusion remarks about this course. We'll discuss if you will have some questions and you'll need something to discuss, we can do it during the remaining part of today's lecture or next week. I don't know if you have some questions or you would like to ask something about today's lecture. If not, I'll feel free to end this show, and I'll as usually collect these recorded material, and I'll send it to you by the sweet transfer file in this group message as I did so far. So if someone who could not be here today with us, he will have an opportunity to see what we were talking about. Okay, that's all for today. Let's stay in touch and for the next week, and goodbye.
Bye bye.
Bye. Have a good day. Thank you.